Good afternoon, everyone. My name is Julia Matevosyan. I'm a Chief Engineer and Associate Director at ESIG. I'm kicking off this session on large load integration and technical issues associated with integration of large loads such as data centers and crypto mining. Before we get started, just one thing I wanted to mention. We have a large load task force happening here at ESIG. And we focus not only on reliability related aspects of large loads, but generally all sorts of challenges and impacts that large loads introduce to power systems. And so the task force consists of 7 topics. We focus on forecasting, interconnection process and studies, interconnection requirements, modeling, markets, transmission planning, and resource adequacy. And so if you are ESIG member, reach out to us and you can participate in task force activities. If you are not ESIG member, stay tuned for reports as they will be coming out starting from the end of this year and Q1, Q2 next year. So you'll see a report on each of the topics and then a couple of supplemental reports just with informational reports on events, capabilities of large loads, and impacts of large loads on the grid. All right, so without any further ado, let's go ahead and get started. We have a full panel here of 5 panelists, and I'll just let them introduce themselves as they present, and we'll start with Amin Zamani, and he'll be talking about he'll be talking about understanding of large loads, induced load profiles, and complications. Go ahead.
Okay, thank you for the introduction, Julia, and good afternoon, everyone. Thanks for joining the session. Amin Zamani with Quanta Technology, part of the Advanced Technology Integration Group. And as Julia mentioned, we're going to kick off this panel with the introduction to the characteristics or power consumption characteristics associated with the large language models. We have all heard about the unique characteristics of these loads, low inertia, high ramp rates, irregular duty cycles, so on and so forth. And we have also heard that this is associated with synchronous operation of the GPUs. So about a few months back, we formed a small team in Quanta that in collaboration with the University of Alberta, they started digging into some of the simulations and performing studies at the GPU level to better understand the characteristics of these loads, with the idea that it would help us better analyze the impact that they can have on the grid, as well as the solution. So what I am going to discuss today is a summary of findings, and I have 15 minutes, so you can imagine how deep I'm going to discuss the topics. But we'll start with a little bit of introduction to LLM and neural networks. The main idea is to create a high-level background to give the context for some of the actual load profile that I will provide later, so different steps. Then we have some result of the GPU level and how it's propagated to the POI. And finally, we'll touch base on the challenges. I promise not to talk about solutions, so my fellow panelists will talk about more challenges and the solutions probably. So with that, we have all heard about these 2 phases of the LLM. Training, when the model trains on a vast data set, it's the most power intensive phase when the model gets prepared for public, and in other words, try to understand how to respond to an input. This is the power intensive because a lot of GPUs needs to work in parallel to train a model. The second phase in the inference, when you send a request to the model, ChatGPT, Copilot, that part is less power intensive and very user dependent. In other words, if there are not so many requests, let's say in the weekend, you're not going to get too much power fluctuation on consumption from the inference phase. What I'm going to discuss is to identify the different parts in these 2 stages that cause some of those spatial characteristics and understand what are those characteristics with hopefully some numbers supported. Again, to understand this, let's build the background. I'm oversimplifying some of this stuff just to get the basic understanding through. So if you are expert, this would be more of a overview for you. Most of these LLM are based on the neural networks, which are layers of interconnected nodes that are designed to classify inputs. In other words, during the training, this neural network try to learn by repeatedly attempting classifying input, processing input, calculate the error, fix the error, get more accurate. Finally, they would be able to recognize a pattern. What happens is that at the initialization phase, this neural network, there are just do the random calculation and guess. And then as time goes, they would get more accurate and accurate. To give you an example, let's assume we're going to do a high-level image classification when we have a bunch of hand-drawn numbers and we want the neural network to understand which one is what. So we start with the first initialization, and as I said, the neural network is going to have a random calculation by processing this data through the weights and the variables of the neural network. This is what we call a forward pass. So remember that term. Then it calculates the error, learn from this error, and try to get more accurate based on the error that it sees, and adjust its weight through a backward path. For this simple example, there are going to be thousands and thousands of these forward and backward paths until the system gets accurate enough. And remember, if I go back to the previous slide, there are iteration too. So the LLM or the neural network is not going to process all of them at the same time. It's going to categorize data, start with these two data that become one iteration, then two data, and does all this iteration until it has the full epoch. So there are iterations and forward and backward passes during this training. The other thing I wanted to mention maybe before inference, for large loads, instead of 1,000, you have billion of these iterations. And that's why the uninterruptible power supply is very important, because if you lose the power, the training load needs to go to the latest saved or checkpoint and is forced to start from that point. So that's going to be a lot of time, a lot of power, which is not desirable. So the second phase is inference, and that's when you have a request to the model. There are two phases for this stage. The prompt phase, when technically the engine start processing the data through the parallel operation, and that's the most compute-intensive phase. The second phase is the token phase, when you process the request and then you try to create the response, the model try to create the response based on understanding in a sequential actions. So if I want to give you an example, let's say you go and ask a question from the chat GPT, pizza is better or bigger. So the first stage is that this needs to be processed, the words, what they mean in context with each other, and that's the most compute phase. When it understands this, it creates the response in a sequential manner, as you see here. Pizza is better, end of sequence. From the power consumption perspective, that's what we're going to see. During the prompt, when you process the data, there's going to be a jump. But after that, when you go to the sequence of actions to create the response, you have a relatively lower power consumption. A big note here is the inference requests are stochastic. That means it's unlikely for the two users to have the same request at the same time. That means it's unlikely for the GPU racks responsible for inference to start together and stop together, which means it's unlikely that we'll have this power spikes for inference to be in phase with each other and create more severe condition in terms of the power profile. So now let's talk about some of the phases that cause this transient in the training and inference. The very first surge is to start with the model initialization. When the data is recorded and allocated, the neural network needs to initialize, and that's where all the GPUs work together. You'll see the first jump. There are going to be evaluation interval. We talk about the checkpoints. When every now and then the model needs to stop, look at the accuracy, have a save point, and at that time the GPUs, or majority of them, go to idle mode and will cause a dip in the system. During the training, those forward and backward paths, and also the iteration, there needs synchronous operation of GPUs. That means some of the GPU needs to wait for others and start with each other, and that's all going to be high frequency changes. Not as bad as interval or the energization, but still you'll see those stuff, and we'll talk about the inference prompt and the token phases. Before I show some of the numbers, let's now see how this is going to be translated to the POI. So what we discussed so far is all at the GPU level, or the VRM here, a very low DC voltage. We have a lot of converters there, and the main job of those is to mainly provide the DC current for the GPUs. They have high bandwidth, those converters, and as a result of that, all the high frequency microsecond level changes will be at that level. The second phase, number 2, is power supply units, mainly responsible for converting low voltage AC system, let's say 415 to 480 volt, to the DC side, which could be 58 to 51 volt, depending on the state of the PSU. The power supply unit usually has 2 states. Got excited, I guess. The first one is the DC to AC, AC to DC rectifier, power conversion rectifier, that regulate the input AC to the PSU and also regulate the DC voltage. It has relatively a slower bandwidth and a smooth out the load. Following that, you have a DC link, which I haven't shown it here, unfortunately. We call it DC link capacitor, 430 volt, and then you have DC to DC choppers that they bring the voltage to 48 to 50 volts, depending again on the mode. That cap bank also helps with the smoothing some of the loads. In general, the PSU will smooth out the load by tens of millisecond range, roughly 50 to 70 millisecond, based on some of the tests that we have done. Depending on the data center, you might have also UPS, inline UPS or a double conversion UPS. They have capacitor, they have rectifiers, they have relatively lower control bandwidths, they smooth out the load even thousands of the millisecond. And on top of that, number 4 is all the reactances and inductances that will also smooth out the load. So in short, what you will see at location 4, the POI is not going to be close to what you have in 1, but it's still problematic. So now let's talk about some of the numbers. Disclaimer here is that these are all at the GPU level, but because I have been involved with a lot of projects when we tested the power supply units, and I know relatively better these animals compared to UPS, we're just going to stop at the PSU when we have developed a detailed switching model of this and verified it against the tests. So let me start running this. Okay, the graph on the top is the DC power consumption, and the graph below is the PSU. First of all, you can see the difference between the frequency changes. The first spike starts at the model initialization here, when all the data is recorded and you have the loading of the data. And then after that, there are forward and backward passes. You see high frequency changes in the DC side and compare it with the PSU. And that's technically what we discussed. This continues until we reach to the end of the one training epoch. Then the system goes to the interval. evaluation interval. Everything is idle, and then the next epoch starts. To provide a little bit of number, again at the GPU level, and with the disclaimer that they are very dependent on the hardware and the training model, and we do understand that there are new AI accelerator that they probably provide the higher ramp rates, although the pattern is more or less the same in terms of all these phases that we discussed. So this is for a, what was the name? RTX 4090, yes, RTX 4090 GPU, 500 watt. And you can see the values, the ramp rate at the DC side and the PSU, roughly 300 kilowatt per second, and the kilowatt is correct, which means 800 per unit per second. At the PSU, that's dropped to almost 60 kW per second, which is roughly about 50 per unit per second. So still large, but it is at the GPU level and the rack level. So this is for the inference. Different model. This is the Gemma model, is larger compared to Llama, the previous one. But you can still see that you have this jump at the prompt level. And then during the token phase, everything is relatively smooth until you get to the next request. Comparing the result, you have 400 kW here compared to 72 at the PSU, and you can see the jump. What I do like again to emphasize is that for the inference, there is a low possibility that you have several requests at the same time, and that's really helps because they're not going to help the or being in phase and create higher spike or dip. So not talk about challenges as I promised, but we do know this is going to be problematic for both sides, the data center side and the grid side. And some of the problems are actually common that needs to be fixed. My fellow panelists will talk about that, hopefully also in the Q&A. And the conclusion, not fully related to this presentation, but what I wanted actually clarify is that we really need to collaborate. The data center facilities, utilities, ISOs, we need to better understand the design of the data center, all these load characteristics, rather than I guesstimate. We need to be aware of those information, and vice versa. We need to better understand or make sure that the end user know the grid requirement. Model and validation is very important. We need proper modeling of the load so we can do the studies properly, and hopefully we can assess the technologies. And that, again, needs us to have a fresh look to some of the other items, including some advanced testing. I did it. Perfect. Is it me?
Thank you so much, Amin. And as Amin promised, now talking about solution is Sergey Kynev. He is a business development manager at Siemens Energy. Go ahead, Sergey.
Hi, everyone. My name is Sergey Kynev. I work for Siemens Energy, and I spent my entire career in a group what design and build the grid stability equipment, and which might be based on rotating equipment like synchronous condensers, or based on power electronics like Statcoms. And what today I'm going to talk about is E-Statcom. Basically Statcom equipped with supercapacitors, which act as energy storage. So I want to continue on a discussion what Amin started on the workload from data centers during the AI training. So I took this picture from the recent NREL white paper report, which shows one of the example of how it's going to look already on the POI. So what grid might see if this load connected without any mitigation measures. And I think on this panel, we will talk a lot about different concerns. Very briefly, from what we see from our side, discussing internally, we can categorize the concerns of this load connected to the grid on system-wide range. So we're talking about general system instabilities, inter-area oscillations. Concerns on a power quality level, like a classical flicker, maybe even harmonics, voltage variability, and one maybe very important aspects, and what I want to dive in a little bit before I start talking about E-Statcom, is the impact of this load on the rotating equipment, which might be connected nearby. And it might be coal, gas, or nuclear, doesn't matter, the physics remains the same. We might see the whole range of impacts of having this load nearby the rotating equipment, and might range from just frequent trips and control instability to more severe consequences of equipment damage and even personal safety risks. So we did internally some investigations of the first question we wanted to answer is, okay, I have the data center connected to the grid, and somewhere nearby, I have a rotating equipment. We took a large gas turbine nearby. And the first question we want to answer is, how much of this fluctuating load will be actually seen by the generator, and how much will be consumed by the rest of the grid? So at which point we will need to start to worry about. So we did a study in PSCAT, very simple, where data center is represented by fluctuating load, where we just vary different frequencies, different amplitude, and different shape. And we found out there is three major factors which impacting how much of the stress is actually seen by the generator terminal. The factor number one is probably the most obvious, is electrical split of impedance. So basically, how electrically close the machine is to the source. So if we look from a data center perspective into the grid and into the nearby plant, so the load will be proportionally distributed between the generator and the grid. And if the grid is weaker, meaning it has a large impedance, more of this stress will be seen by the generator and less by the grid. And if we take an extreme example where it's an off-grid island type of situation, 100% of this load will be consumed by the generator. So this is a factor number one. The second factor is the frequency of the load. General rule of thumb here, the higher the frequency, the worse it is, because the generator reactance also changes with the frequency. It moves from synchronous to transient to subtransient, so the XD, XD double, XD dash, and XD double dash. So this plays a role. But what I'm showing here is one of the effect of if the load hits so-called electrical resonance, a local mode, right? So every machine will have a local mode, typically somewhere around 1 Hertz. And if the frequency hit, if the load hit this frequency, it's no longer just proportional distribution between the impedance. You start to see an additional fluctuation between the generation and the grid. So all sort of instabilities will happen. And this is not just some theoretical frequency, right? If I go back to this graph published by NREL, what we see here is a big dip exactly every second. So there is a huge 1 Hertz component already. So this is a factor number two, and factor number three is the ramp of the change. So Amin mentioned this. We are talking about millisecond change of a scale of megawatts, and the ramp plays a huge role into the stress what machine experience. So on this graph, you see the load having exactly the same shape, same amplitude, same frequency, but a different ramp of the change. And this already produce a very different stress to the machine. We are talking about igniting all frequencies very often, even if it's not in a seconds, but if it's every minute or every 2 minutes, this is already way more than a machine is designed to. Right, so obviously this type of load cannot be connected to the system as we have it right now without any mitigation measures. Let's talk a little bit about this. So once we start to think about mitigation measures, the first question we need to answer is what is the acceptance criteria? What do we want this load to look like? We cannot just write in a contract, it needs to be smooth and steady, right? We need to have some numbers and some quantitative analysis, and I know some panels will talk about this. So once this is established, we might think about different mitigation measures, which are typically lies inside the facility of a data center or at the POI between the data center and the grid. I'm not going to talk about any of the mitigation exist at the GPU rack level, but from an energy standpoint, the most efficient way to reduce the fluctuation is to add some type of an energy buffer between the load and the rest of the grid or the plant. And this is exactly what we are proposing to do with the E-Statcom. So what is E-Statcom? E-Statcom is part of the facts devices, part of the devices what utility procure for reliability services. Some of you might be familiar with STATCOMs, which are devices focusing on a voltage control and reactive power support. So this is a typical reliability type of device what utilities would procure. The letter E stands for energy, so we are adding the energy storage in form of a supercapacitors to this device. So no, it's not just voltage control and reactive power support, but also the active power component to this. So the supercapacitors has a lot of advantages, and it's a bit of a niche type of energy storage when you need something which need to cycle a lot, charge and discharge with a large amplitude, and do it a lot, but not necessarily for a long time. So we're talking about events which last a few seconds, and the load profiles like we're discussing would be the ideal match for supercapacitors. And the second aspect of STATCOMs is the way we build the converters. So this is a large type of MMC converters, which build a little bit differently from what you might see in a photovoltaic or BESS. This is one large converter, which extremely important here is the response time, right? If we are talking about compensating something on a subsynchronous oscillation level. Last time I presented this was actually on ESIG 6 months ago, and most of the questions been about the control philosophy we use. So I added a slide to clarify this a little bit. So the E-Statcom as a product comes with two different control philosophies. One is the grid forming, which is typically used for utilities to provide inertia services like a virtual synchronous machine. And when we try to apply the grid forming approach to this problem, we quickly realize what it does help, but it might be not the most efficient way to deal with the load fluctuation. And the reason for this is grid forming itself does not directly react on the load change. It reacts on the phase angle and the frequency which is caused by the load change, and it reacts proportional to the impedance, right? So it's quite effective if it's connected very, very close to the source, so on a low voltage side on a rack level. Once you move farther away behind the medium voltage transformer, the efficiency will be way less. And once you move to the high voltage side at the POI, grid forming will not provide that much of a compensation degree. The control philosophy, what we utilize here is actually the same one we've been using for the last 20 years for arc furnace compensation, because arc furnaces has a very similar problem, and it's very straightforward approach. Is basically you measure the load and you react on these measurements. So if the load jumps 100 megawatt, you compensate all 100 megawatt exactly. But for this, you require a very quick response time. And this is what we could achieve based on the example from NERC, right? So no longer the grid need to deal with blue line, but with the green line. And the E-Statcom through this operation will charge and discharge, making sure the state of charge within the supercapacitors are somewhere in the middle. So it can operate like this 24/7 for days and months, smoothing this type of load profile, right? And I want to end with what E-Statcom cannot do. And this is, if we zoom out a little bit, we are talking about supercapacitors, which again has a lot of advantages, but it's a short-term storage, right? So if we zoom out of, and imagine the blue line is a load profile from a data center, and let's say it moves very slowly. It's in a minute time scale. So if there is a minute time scale ramp of a data center up and down, E-Statcom will not try to resist this type of ramps, right? So what E-Statcom is for is to make sure there is no abrupt and quick changes which are happening within milliseconds. Like in these examples here, if the load jumps or drops extremely quickly, what E-Statcom will ensure happening, it's no longer a jump, but it's a ramp, right? It's a more grid-friendly ramp which does not possess any risks to the rotating equipment, and typically it's slow enough for gas turbines to follow. But for example, in the islanded cases, in the off-grid scenario, right, it might be not enough. And what we see a lot of developers are doing is complementing E-Statcom with a regular BESS solutions, which just follows the green line and making it smoother. So basically leaving E-Statcom to compensate the quick load variation happening because of the AI training and deal with like minutes and hours by BESS or other solutions. So this is what we see people are doing most of the time right now. Yeah, I guess this was my last slide. Thank you very much. I'm right in time. Yeah.
Thanks so much, Sergey. So next on, kind of continuing on what do we do with this rapid fluctuations and how this may translate into requirements is Andrew Isaacs, who is Vice President at Electranix. Go ahead.
Good afternoon, everyone. Everyone's still a little sleepy from lunch, hopefully. Shake out your shoulders. And so these loads, yeah, my name is Andrew Isaacs. I work with Electranix, consulting company in Winnipeg. And one of the things that's happened in the last year or so is that gradually the amount of emails related to large loads in my inbox has gone up. So I'm spending more than half of my time on this now, and I can't really decide whether this is interesting and exciting or whether we're all just on a train heading over a cliff and I should probably just retire and go live in a cabin somewhere and let the world deal with this stuff. But anyway, it's a big issue, and I think everyone is worried about it from different perspectives, right? Loads are worried about it because, you know, this is their business. This is what's happening in the world. It's a global thing. And obviously power systems engineers and utilities are extremely worried about reliability. And so we've been doing a lot of thinking about requirements and working with utility and ISO partners to try and find the balance between reliability, maintaining reliability, serving these loads which need power, and not driving cost up too much. But all of these things are kind of conflicting with each other. And we're struggling with a number of things. So this presentation is not going to probably give you a lot of answers, but if you are thinking about requirements and what needs to happen in your transmission grids or what might be coming down the pipe, these are some sort of philosophical ideas about how to think about requirements and what might work for your system. And it's important to remember that good requirements are not generally the same everywhere. A requirement in one system is not going to be the same as a requirement in another system. And so we're in a bad spot in the industry right now where we don't have requirements to borrow. When we're trying to come up with a new thing, power systems engineers look for standards and they look for other utilities who've done it first and they look for lessons learned and all of that, and there are none. And so the first ones that come up with this sort of stuff are sort of examined closely and we have to learn from them, but be careful not to just copy. Okay, we have to think about this. So this is hopefully going to help you a little bit with that. So I want to summarize the categories of risk that we're dealing with that might drive requirements first. So we've heard about these active power variations. Synchronous generator damage, we're quite worried about that, okay? This isn't necessarily a theoretical problem. We've heard rumors of generators being damaged in the industry next to these AI loads. Everyone's quite closed about this topic right now, but it's a genuine concern. I hope that we're all wrong and this isn't a problem, but it looks like it might be. Flicker is a problem. Machine mode oscillations, I think Sergey touched on. Inter-area oscillations are one that we tend to not want to talk about too much because we're not very good at doing these studies in North America already, and this could be a new problem. So that's all under the category of active power variation, okay? We're also worried about ride-through failure, and failure to ride through for these loads. In the past, we don't really talk about load ride-through capability. This is a new thing, but we're now worried about load rejection over voltage. We're worried about VAR adequacy or control of the voltage. And we're also worried about resource adequacy, okay? And it could be including frequency control as well. And we're also worried about passive damping. So this is something that if you live in Texas, you've heard the letters SSCI put together before. That's been a major issue in series compensated systems. This is going to layer onto that issue, okay? So that's not good news. We also think about power factor, modeling requirements, verification, and I think in the future we'll be talking about voltage control and frequency control from these loads as well, damping control as well. But I want to focus today specifically on the active power variation and ride-through failure. So there's different philosophies that we can take when we're writing these requirements or when you're implementing a requirement. First, you could say, essentially, we're going to make this an individual requirement. Every load comes in based on, and they're allowed to do up to a certain limit based on a study, okay? So you do an impact study for a load, consider all of the system around you and the synchronous generators and the load profiles and the voltage profiles and everything, and then you set a requirement for that load based on those studies. The second approach is to say, we're going to make a blanket requirement, so basically a screening guide or a very low or a relatively conservative requirement for everybody. And if you meet that requirement, you're done. We're not going to study it any further, okay? If you don't meet it, or if you feel like you need to do somehow more variation or an exception to the ride-through criteria, then we will then do a study, okay? So you have to be, you'll be subjected to a detailed study if you can't meet the screening guide. And the third approach is to say, we're not going to do any studies. Here's the requirement for load fluctuation and ride-through. We're not going to study anything. You have to meet this requirement or you may not connect, okay? So those are three approaches, and each of these may be the right one for your system. Okay, and you can see how tending towards larger systems or more complex systems, you would want to start to avoid doing studies. And you would lean towards the blanket requirement. And if you have a relatively simple interconnection or very few loads connecting, you might be interested in the left side. So the pros and cons. The pros of an individual requirement are that you have maximum load flexibility. Okay, you can really extract the most possible out of the load and use your system to its limit. Okay. The con is that it's a very heavy study burden, and we'll talk a little bit more about these studies, but they're not easy studies. And in some cases, our normal process for doing a study is broken by the fact that we have a difficulty coming up with a pass-fail criteria. Okay, we'll talk about that in a minute, but the studies are difficult. Restudy might be needed if the grid or load changes. So you've done this big detailed study and now somebody changes something, you may have to restudy it. And you may find yourself using up all the available margin in the system. Okay, so all of those are not great. If you go to a blanket requirement with exceptions, now you can quickly accelerate the load interconnections if folks are compliant. So if people are meeting your requirement, now you can relatively quickly connect loads without doing study. The downside is that the study burden is still heavy because many of those loads early on are not going to be able to meet that requirement because it's probably going to be narrow. You will have to also, again, reevaluate if things change. An important consideration when you're talking about this one and the third one as well is that depending on where you set your threshold, you may be exposing yourself to risk. Okay, you might not have considered all the boundary conditions, or you may have had to be conservative, but not overly conservative. And so some of the edge cases might slip through, or you may have missed on your criteria screening, and now you have an issue in the system that you didn't catch. And again, you might find yourself filling up the margin that you have available. For the third requirement, the obvious advantage is we don't have to do study. Okay, and that's a major advantage. And it also generally will accommodate future changes. But now we have two kind of conflicting problems. We have the possibility to over-constrain the system or over-constrain the loads. So now you've set such a tight criteria that loads are now having to either spend a lot more money to mitigate it, or they're not able to connect at all. So theoretically feasible projects are now going to fail. On the other side, you're going to potentially have to relax that ultra conservative criteria, and you're going to miss issues if you've set those criteria too loose. So there's no perfect solution you can see here, but I just wanted to mention on the studies to consider, studies are our business, and we really like to have all of the data we need. We like to have the models being accurate, like we talked about this morning. And we like to have a clear definition of success when we're running a study. So is it stable or not stable? Did it ride through or not ride through? Did it, exceed some limit? These studies, we don't have that right now. So data is very hard to get, first of all. The load variation limits are very difficult to get and sometimes unknowable. Harmonic profiles are sometimes unknown, at least early on. We don't have sufficient model quality to evaluate damping in the system right now, and there's a number of other model issues. That's another topic we're not going to get into. I think actually a later presentation might talk about it a bit. And ride-through capabilities are also hard to get, and some data is extremely hard to get or maybe impossible. Multi-mass data for a machine you can probably get if you have the right levers to pull, but the synchronous machine physical design limits are going to be a real challenge for you to get. And so that happens to be our pass-fail criteria. So if you're trying to do a study every time to show whether or not this load is going to be okay for your synchronous machines, how are you going to know if it's okay or not if you don't have the physical limits for that machine? Okay. The other thing about studies is that they're complicated and they're time consuming. And so you're going to need some specialist skills and a lot of time on your hands. A couple of different frameworks, running a little bit out of time, so I'll speed up a little bit, but there's different ways that we can set up these criteria for active power variation. I'll sort of highlight two ideas on this. I'm still not 100% sure which is the best one. They have, again, pros and cons. The first one is to say, well, we know we're really worried about certain frequency ranges, right? We're worried about subharmonics or subsynchronous range because of the synchronous machine torsionals, and we're worried about machine mode oscillations and so on. So we could say, for these frequency ranges, you can have a fine filter or a wider filter, but for these frequency ranges, limit the magnitude of the frequency content of the load active power fluctuation. You can get quite sharp with those criteria, and you can probably allow fairly large variations in active power that are avoiding the key frequencies that you're worried about if you do that. So that's the pro. The con is you're going to have to be very careful how you specify those criteria. You have to be careful with how you measure the frequency content, how those frequencies might interplay with each other. For example, a step change or a spike will contain many different frequencies. Each of them, the magnitude might be small, but the overall spike might be interesting to you. And you might also have to monitor and enforce this, and it might be difficult for people to understand looking at a plot whether you're violating the criteria or not. The second framework idea is to say, just put an absolute limit on the magnitude variation. So the active power is going to be moving up and down. It may not move more than, for example, 25 megawatts peak to peak in a 5-second period. It's very straightforward to implement. You could take this green box and just sort of slide it along the plot, and you'd be able to see whether the load profile was meeting it or not. The difficulty here is that you may overconstrain the load. It might be hard to choose all those problems that we mentioned before. It might be hard to choose a single value or even a set of values that protects equipment adequately in all cases without overconstraining the load shape. Thinking about ride-through framework, you can use a ride-through profile similar to what you might see in IEEE 2800 or some other ride-through curves that you've seen. But you need to think carefully about what you mean by that and what those criteria might imply. For example, for that ride-through curve, are you allowing them to temporarily block their active power and then come back after a certain amount of time, like 1 second, or not? Because if you're thinking about, depending how you think about that, you'll be impacting all of those things we talked about, load rejection over voltages, especially load rejection over voltages where you may have many co-located plants which have a very sensitive undervoltage threshold. You might find yourself tripping 4 loads in the region rather than 1 that you thought you were studying. And also consider when you're writing this criteria and also other criteria is that initially, probably none of the loads are going to be able to do it, okay, or very few of them. So what are you going to do when you write a requirement that nobody can meet? It might be the right requirement and it might be a needed requirement, but if no one can meet it, the pressure is coming on you to either make an exception or mitigate that some other way and basically bend the rules somehow for this load, and that's going to happen. And so you have to think about that. And usually, the answer to that is it's a phased approach, or it's a we'll mitigate for now, or we'll do a study or something like that. But it's messy when that happens. I'll just leave you with an example requirement that's out there. ATC was the first sort of full-throated requirement of this type that I was aware of. And it is, it's 2 parts. I put the link in here. It is a blanket requirement with exceptions. So they've taken that sort of middle road, and they're using an absolute magnitude variation over time, 25 megawatts over 5-second period. And their their voltage ride-through criteria is something like this. It's a modification of the 2800 IBR ride-through criteria with some changes based on their system, and some guidance around what they mean by ride-through. Their active power criteria applies. Oh, it looks like we lost the 200 there. Loads greater than 200 megawatts, that's supposed to be. But the active power oscillation limit is in 2 parts. The first one is the 25 megawatt band. The second one is above a certain limit, in this case 50 megawatts. If the active power changes more than 50 megawatts, you'll have to ramp the load at a fairly slow ramp rate. So this is a sort of a type of ride-through requirements, basically trying to allow the operators time to adjust their system. And these are values for the aggregate of all loads connecting into a location that may be synchronized. So it's not on a per load basis. This is going to be the total load going into the system. So already there's going to be drama around this one, and the loads will feel it's too strict. Certain studies will indicate that this might not be strict enough. If you apply certain types of load profiles, you can potentially still damage a shaft and so on. In the area, it's very important to realize in ATC that the generator owners have been part of this discussion the whole time, and the loads. And the generator owners, in order to hedge their bets, are also putting in additional monitoring equipment for oscillations in their plant. And they'll be looking at, over time, what do these frequencies actually look like in their system, and potentially even operating relays based on what they see. So they're not taking chances in that way. Okay, I think that's all I got for now. Thank you.
Thanks so much, Andrew, and kind of continue the topic of need for studies and modeling. We'll hear from Shahil Shah, who is principal engineer at National Renewable Energy Lab, and he'll be remote. Lacey, would you help us out here?
Hey, Julia, can you confirm that you're able to hear me?
Yes, I can hear you.
And
that means you can share your slides now.
Yeah, let me share my screen. Do you see my screen?
Yes.
Okay, yeah. Hello, everyone. My name is Shahil Shah. I'm a principal engineer at National Renewable Energy Laboratory. I was thinking that I'm going to go last, but looks like I'm going second to last. But it's always good to go towards the end so that I don't need to repeat a lot of things. In this presentation, I'm going to talk about data center power system architectures and modeling. My focus is really on modeling. Andrew touched upon the modeling data is not easily available, and also there are a lot of challenges and variations. The technology is evolving very fast. So the core of this presentation would be about how to model data centers and what are the key considerations that we need to keep in mind. So I'll start with different factors that influence the modeling, data center modeling. Again, just to emphasize, this is not a large language model. I'm talking about power system model that we use for grid studies. I'll touch upon the data center power system architecture, like how the typical architecture looks like from point of interconnection to GPUs and CPUs. What are the new architectures coming up, modeling considerations, some small signal stability issues, some work done by Meta to mitigate oscillations that they experience in the data centers during the last decade. And if I have time, I'll go and show some video of megawatt scale demonstration at NREL of these torsional oscillations. So in terms of factors that influence data center modeling, one is, of course, on the right, model application. What do you want to use this model for? Is it just the load profile, which has been the topic of many of the previous presentation, and to understand its impact on different issues like torsional oscillations in nearby generators or flicker? Are you looking at transient behavior, loss of load, LVRT, right through, or also the dynamic interactions like oscillations, weak grid stability issues, control interactions? Depending on what is the objective, the model can look very different. You can make a lot of simplifications if you are focusing on a narrow type of study. But if you want a model which can be used for all these things, then the model can be very complicated. The other part we need to consider is the architecture of data center. And there are two parts: power delivery from POI to IT racks. And the second is what is inside the IT racks. Within power delivery, AC UPS is the one power electronics converter that we all talk about. There's also talk about having a DC UPS to reduce conversion stages, a solid state transformer, a sidecar where you put all the power supplies outside of the IT rack, but put it in a different rack where to basically have enough room within the IT rack for GPUs and CPUs or server nodes, and the non-IT load. So those are there are many variations that we should be mindful about or consider. And on the IT rack, like what is there within the rack? Right now, the industry is using 48 or 50 volt DC bus bar voltage for supplying these racks. But then there's a lot of interest in new developments, real commercial technologies on 800 volts plus minus 400 volt DC, again to fit a lot of GPU power and compute power within a single IT rack. So if depending on which bus voltage we use, the data center can look very different. And then PSUs that can be within the PSUs which supply data centers, there are different topologies. And then few new technologies like BBU, battery backup unit, and CBU or capacitor bank unit, which I'll talk about soon. So let's start with architecture. This is how a typical horizontal data center looks like. The vertical data centers are hard to see what is inside, but the horizontal, when you have enough land, it's easy to see a lot of the high power components. We have high voltage and medium voltage transformers, diesel gensets for backup, and then we go inside the different data center pods or rooms, which will have the AC UPS and all the IT racks. So this is what we were seeing in the previous picture, where we have high voltage and medium voltage transformers, and then the AC UPS, which are again tens to hundreds of them in a typical data center. They are located with the data center room or pod, and then they supply to the server rack. And I think this has been discussed a lot. What I want to focus more on is like what is there within the IT rack. So we start with 480 volts today. Previous data centers were more towards 208 volts. And then we have this power supply units, very long, which you can hot swappable, which are arranged in something like this power shelf, where multiples of three are arranged in a single power shelf, multiples of three because they're all single phase converters, but they are supplied by a three-phase supply. So they're distributed either using star or delta connections. And then they have a AC to DC conversion, medium voltage or a middle level 400 volt DC, and then a DC-DC converter to provide 40 volt output. The power rating of the PSUs are increasing, 3.6, 5.5 kilowatt, and now I also saw recently a 7.2 kilowatt PSU. The size of IT racks is growing. The biggest one that I saw recently is a 300 kilowatt rack. So a single rack consumes that much of power. So this is about a typical architecture, about where we use 48 volt DC to supply IT racks, and then AC side feed at 480 volts. But then there are new technologies coming up, as I mentioned previously, that looking at 800 volts DC power racks. And this 800 volt DC is coming both within the power delivery between POI and IT racks, and also within the server. So solid state transformer, for example, if we have that, then we need to change again our model to look at these things. Very interestingly, the storage is now pushed into the IT rack, for example, battery backup unit. So if you're using a backup within the IT rack itself, you will not need AC UPS or DC UPS for the compute load. You might still need it for cooling and lighting loads. And I've seen both variations where some data centers, they don't ask for separate AC UPS or DC UPS storage because they have this backup embedded within the IT rack. So again, this is another variation which can impact how we model data centers. We talked a lot about the load profiles or the load fluctuations. And there is this new development capacitor bank unit, CBU, which again goes inside the IT rack. And its main function is to smooth out the input current. Basically, it absorbs all the load variations at the IT rack level itself so that it doesn't impact the grid. So these new developments are again led by the front runners of AI companies They are not, of course, going to be adopted by universally, but we have to be mindful about that, because if you talk about load fluctuations, there are some solutions not only at the POI side or behind the meter, but within the IT rack itself. So that needs to be considered in the model. Switching gears a little, so now, okay, how the AC UPS operation mode impacts the modeling. So there are three different operation modes. One is a double conversion mode where power flows directly through back-to-back AC-DC AC converter. In this case, the grid will see AC UPS first. It will not see the PSUs and IT racks. So it makes our job as power system engineers a bit simple, because we can look at this multi-megawatt converters, which looks very similar to inverters in battery or PV power plants at the front end. The second mode commonly used, or which is now becoming more common than before, is the bypass mode to save on the losses, where the UPS is bypassed by a static switch. In this case, all those hundreds of thousands of power supply units, they'll directly interact with the grid, and their modeling becomes more critical. So depending on what is the mode used by a UPS within a data center, the model structure can look a bit different. There's a third mode. I don't think it is very commonly used, where you have a UPS is bypassed, but the load side converter is still active to provide power quality, in which case we need to focus on both modeling of IT racks or PSUs within the load, as well as this load side converter in the AC UPS. So to summarize, we have two main converters in the typical architecture that interact with the grid from data centers. There are different types of converters, but these are the two main, AC UPS and PSU. Depending on whether the AC UPS operates in a bypass mode or double conversion mode, we need to focus on either of these two. And another challenge, which makes things a bit more complicated for data centers compared to inverter-based resources, is the number of power converters. Like PSUs, there can be hundreds of thousands of PSUs in a typical data center. So how do you aggregate them? It's not just like I model one PSU and then scale it to a very large level. So that's a challenge on aggregation. And as I discussed some new technologies, they can completely alter the architecture or structure of data center power system, and then we need to account for those things in the model. So let me go into this small signal stability real quick and talk about some specifications which are developed by Meta. So we have seen a lot of these oscillations on the grid side. ERCOT had this in the presentations. Dominion Energy has released few examples of this. Not widely known, but Meta experienced some oscillations at a broad frequency range at 11 hertz was to several kilohertz within the data centers in 2018. And then they resolved this problem in 2020 by developing some frequency domain specifications. So what really was the core of the problem was that the PSUs were interacting with the grid, and we need to look at the broadband impedance response or frequency domain impedance response to understand how the data center building was interacting with the PSU. I'll probably skip this slide, which just shows how we can have subsynchronous oscillations because of interactions between all the IT racks and the grid. This is similar to what we see with IBRs. The problem is, again, negative damping because of active controls within this frequency range. But in the interest of time, let me quickly cover the specifications from Meta. So because they saw these oscillations in around 2018, 2019 timeframe within the data centers, the outcome of the analysis was that some of the IT racks were interacting with the power supply, which was basically the data center building, right from grid POI to all the transformers and then up to the terminal of the IT rack. They came up with this term, base impedance ratio, or I think it is building impedance ratio, or maybe it's base impedance ratio. This is very similar to the short circuit ratio that we use for in power system studies. The base impedance ratio is basically the ratio of base impedance of PSU, depending on the rating of power supply unit, versus the actual building impedance. And then the building impedance is mostly inductive in nature because of transformers as well as additional inductors that are inserted to limit fault currents. So the requirement focused on this BIR, which is again similar to SCR. And then the requirement was focused on, or is focused on, both building side as well as the IT rack side. So for the building, we want to design the building which provides high BIR or high SCR. So basically, there shouldn't be a lot of impedance within the building or within the distribution network. So if IR is more than 2.5, it's considered as pass. And then as you go lower, you basically make the grid weak in a sense for the IT racks. There are similar requirement for PSUs where we want PSU to remain stable even for BIR, which is less than 1. So we are really talking about really weak grid conditions compared to if we look at it in a frame of reference for of SCR that we use. So Julia, can you tell me how much time I have? Sorry, I stopped tracking the time.
5 minutes.
Oh, okay, great. That's awesome. So with that 5 minutes, I would like to cover this megawatt scale demo that we did at NREL, which is not really related to the modeling requirements that I was talking about. What we did was we emulated data center load profile using a 7 megawatt grid simulator that you see on the right, and then supplied this emulated data center load profile using 2.5 MVA synchronous machine, and just wanted to demonstrate this oscillations. Of course, I mean, it's no magic that the shaft will oscillate if you directly supply such a highly fluctuating load from a synchronous machine. But there are two objectives. The one objective, of course, was to demonstrate this oscillations and how storage or any other inverter-based resource can mitigate this oscillation. But the second was to demonstrate the ability of creating this load profile so that we can use this load emulation capability for testing power electronic equipment used in data centers like AC UPS or solid state transformers. So here is one video that I would like to play where the blue line here is the natural gas generator output. We configured that 2.5 MV synchronous machine as a natural gas because we are using an industrial controller, the governor control. So the mode that was selected was a natural gas, and the red or the orange here is emulated load from one of our grid simulator, varying between 200 kilowatts to 1400 kilowatts. And then we also had a battery in this setup, but in this particular case, the battery is not doing anything. It's just not dispatch. It's just a grid following battery connected over there. So and on the left is the picture of a shaft where we are using a stroboscopic camera to show the shaft. So if the shaft is running at a constant speed, we will not see any oscillations. It will look steady because the frame rate of the camera is proportional to the speed of that shaft. But as we are seeing that the shaft sees a lot of oscillations, and then as we can also see that in the frequency, the electrical frequency at the output of synchronous machine, that there's a lot of variations. Now, in this particular case, we dispatch battery, use measurement from the load, and dispatch battery to basically absorb all the fluctuations so that the natural gas generator output remains steady and the variations are absorbed by the battery so that we don't see this impact on the shaft. And this was something I think discussed in a previous presentation. So as you can see in this case, in this video, that the shaft is very steady and it's not experiencing all those oscillations. So yeah, that's the summary for this particular demo was that we can use battery storage, but it can be storage within IT racks, within at the POI behind the meter, within the UPS also, which I would think would be more efficient because you are in a way removing this firewalling grid from the load. But the main consideration would be how fast you are able to absorb those fluctuations, how fast you are able to measure the load fluctuations and then mitigate those. We have started a couple of new projects at NREL on data center stability. One focuses on the first part of what I talked about, development of EMT and phasor models of data centers, generic models which can serve as guideline for the industry to develop model intake requirements, which we can then use for vendor-specific models. And I believe that over time, once we are able to get those vendor models, we don't really need to depend on so much on generic models except for planning, development, stability tools, performance guidelines. And the second set of projects are really, we are collaborating with some power electronic equipment manufacturers for testing their equipment for data center loads, just like AC, UPS, and solid-state transformers. So I'm looking forward to sharing the products from these projects. Thank you.
Right. Thank you so much, Shahil. And continuing the topic of stability and operation considerations now for off-grid data centers, Naresh Acharya, who is a technical director from GE Vernova Consulting Services.
Thanks, Julia. Good afternoon, everyone. This is Naresh Acharya from GE Consulting Services, part of GE Vernova. So today, we want to touch upon the topic of the off-grid power systems for the data center applications. Recently, since last 1 year, we have seen an increased interest in developing a system which is completely islanded from the grid, to accelerate the demand for the power for the data center need. So the initial phase of these projects, which are currently in process of planning, will be fully islanded over the period of its operations. Sometime in the future, they will potentially get a grid connection, but in the beginning, early operational years, these projects will be islanded. So as we start talking about the islanded system, we need to understand certain characteristics of the data center load, particularly the AI load, and certain characteristics of the data center itself that we need to understand so that we can build a system that is reliable. The objective of this power supply system is to provide a power at the point of connection with the same level of reliability as the grid, to meet the either the 3 nines or the 5 nines reliability requirement from the for the data center side, right? So in terms of the organization of the presentation, so we will start with our understanding of the challenges imposed by the data center load. It's nothing new than what previous presenters have already characterized, but I think it's worth mentioning one more time. Then we will look at the high level, more simplistic, the architecture of the power supply system itself. The components is very basic so that everyone can grasp what is involved. Then we will talk about what is a problem when we talk about the islanded data center. Is basically boils down to the problem with the frequency and the characteristics of the load. So we will discuss some aspect there, and we have some examples based on the simulations that we did. Although the profiles are kind of generic just because of the confidentiality, so we just mock the profile to show some of the issues the load will provide when we look from the system side, right? We look at the profile issue, we'll look at the fault issue, particularly caused by the load drop due to UPS. And we also have a summary table based on our learnings on what are the type of risks that we see, and what are the cause of those risks, and what the potential mitigation can be. Those mitigations can vary depending on the project needs. Some specific solutions may not be applicable. Whatever we considered may not be generic to be applied to other projects, but depending on the project need, those can vary. But we have kind of a summary table based on our learning, and then we'll just conclude. So when we talk about some of the challenges with the data center, and the first one is obvious. We all know that when the data center is during this training phase, it has a profile where the amplitude varies significantly, and it will be continuously pulsating at a certain frequency, right? Normally, we have seen like a 1 Hertz pulsation where the amplitude can vary anywhere from the 60% of the rated load up to 100% in a matter of cycle, right? So we're talking about the load pulsing in a matter of cycle. From the power generation of the system point of view, this pulsation will act like a big, large step when the profile first starts, right? So our generation systems would be able to absorb that pulse through various means, right? The conventional generation cannot absorb the pulse, so we need some energy storage or some kind of means to help facilitate the transition so that that large step can be absorbed by the system. And this pulsation also has the impact on the torsional aspect of the shaft, particularly if it has a frequency content which coincides with the torsional frequency. And that is a significant risk, and I think this has been discussed previously, that such considerations is an important part. The other aspect, which is one of the characteristics of the sensitive data center load, is the non-fault write-through aspect, right? Now the percentage might vary anywhere from 70 to 85% of the data center load are IT load, and those IT loads are protected by their own uninterrupted power supply, and those power supply are very sensitive to the power quality event. So what that means is whenever we have a disturbance in the system, whether it's a fault, even a temporary fault that causes the voltage to dip, we expect to lose a large percentage of the load from the plant side, right? So it's like a big load thrower event that the plant has to absorb, and that is a risk. On the grid, when we are grid connected, it causes a large drop in power. Now, if the size of the system is big enough, those power is being absorbed by the grid. That's why we don't see these issues yet, although there are some report from the NREL regarding the issue that was shown in the Maryland area, right? So this non-fault through write-through characteristics of the load, together with the UPS tripping based on this frequency and the voltage threshold, causes a big problem when we're talking about the islanded power system. And also, there's another characteristic of the load that we need to understand is power electronics load represent a large portion of the data center load, and this load tends to have a very low damping, right? Because it's a constant power, constant current type of load, so it has an inherently negative damping characteristics, and that can sometimes trigger the modes that can grow in oscillations, causing the damage to the shaft of the turbine generator. Again, we are not going to talk about the torsional mode here. Last week, our colleague presented during the ESIG webinar on this topic, so I think we can go back to look at that. And the last aspect is the load demands very high reliability, which means like unlike other islanded systems like LNG plant, mining, we cannot plan to curtail the load whenever we have an outage in the generation side or the power supply side. So the system has to be highly reliable without counting on the load to provide any curtailment relief, right? So these are the challenges that we have to deal with whenever we talk about the islanded power systems design considerations. And the solutions may require a system-wide solutions, right? So, okay, let's look at the high-level architecture of the islanded system is very simplified just to convey the concept, right? It's basically consists of conventional unit. In this particular case, most of the system that we have seen, it will be powered by the heavy-duty gas turbine, although there are projects where there will be a small aero units, multiple of them connected. And there will be some reserve units to meet the reliability requirement. And now because of the aspect related to the load, the system will require, now depending on the applications, either the the best system or a STATCOM with the supercapacitor type of solutions, depending on the application of the BESS itself, right? So some of the projects that we have been seeing, the BESS has basically a dual role where it is acting as a reserve to absorb the large transient caused by the AI load, and also is helping to mitigate the variations, right, caused by the load changes. Some of the other aspect that that's part of the architecture is the EMS, which basically is like a higher level coordination system that assigns the responsibility between the BESS system and the natural or the conventional generation systems to dispatch power balance on the longer time scale. On the shorter time scale, when it comes to the millisecond level response, it is basically the relief will come from the BESS system. Right? So in this context, we are talking about the energy storage systems which are grid forming, and I think previously there are some discussions regarding grid forming versus grid following and what is best for the system. These applications rely on the grid forming because it allows the synchronous system to provide some relief to the inertial response and minimizes the overall size of the BESS, right? So we can have two kind of design where one where we can use the BESS or the STATCOM solutions to fully mitigate the fluctuations where the size will be larger because we have to fully compensate the load. The other is where we allow the BESS to act based on the frequency change, and that will count on the fact that the synchronous system inertia will also help support some of those transients, right? Now, so one of the aspects that is important to the R&D system is the frequency. So we all know whenever there is an imbalance between generation and the load, it will cause the frequency to vary or the speed to vary. And this is particularly important because of the large transient caused by the training of the AI load. And as described earlier, when the training first starts, right, it appears as a large step, and that step can vary from anywhere from 25 to 40 or 50% of the rated load. So the system without any compensation will experience a severe under frequency event, and that should be considered when we design such systems, right? And also there are other considerations due to load loss whenever the UPS in the data center trips or picks up the load, causing a significant large load flow event, causing overfrequency. So in an R&D system with data center load, we expect to see both issues, one with the overfrequency and the other with the underfrequency, and the solutions, whether it's the hardware or through the operational solutions, would account for both of these issues. So we do have few examples to show what problems these load causes to the power supply, and how we can address that. The one on the left, see when we have the pulsating load. The first chart on the left is the load that varies. And in this particular example, the variation is around 25%, right? So when we have a system with only gas turbine units, for example, the 25% load step, which is modest, right, given the type of profile that we have seen, causes the frequency to dip below 5%, right? And this 5% typically is the threshold where the UPS starts to pick up the load. So which means like if you don't have any other mechanism to compensate, this profile will cause the load to be lost from the plant point of view, right? And this 5% is also typically the point where other equipment start tripping, the plant auxiliaries, even the protection in the gas turbine itself, right? So we know these load profiles are not good, are not friendly. So one of the means to mitigate this problem is to have an energy storage systems or a STATCOM type solutions. Now, energy storage solutions in this particular case, because it has dual role. One, it is used as a backup to provide a relief until the cold reserves are started, which takes anywhere from 20-30 minutes or so. So this BESS system is designed to provide a dual purpose. And we can see from the chart on the right, so when we have the BESS system that reacts based on the change in the frequency that you see at the terminal, it can compensate for that large load loss so that the generation system is stable and we can contain the frequency within acceptable limit. The other aspect is regarding what happens when we have a fault or a disturbance in the system that causes the voltage to dip. The chart on the left, the first one is a fault. It doesn't have to be a permanent fault, even a temporary fault on the grid. Whenever the fault voltage is below the UPS trip threshold, which is typically anywhere from 70% to 90%, 70% to 80% of the data center load will be picked up by the UPS, which means like from the plant point of view, the one shown on the middle left, right, the load will be dropped, right? Significant load drop, 70% load drop from the plant, right? And what this causes is the rate of change of frequency will rise very fast, right, to a point where it becomes uncontrollable, right? So all the generation unit will trip when the frequency crosses a certain point, normally 5 to 6% range, right? So this UPS sensitivity to power quality event, and which is also related to the non-fault factor characteristic of the load, is a problem from the plant design, right? One of the solutions to the problem is basically like an operational solutions to save the system from complete collapse is to trip your generating asset that you have on the plant side, right, to stabilize the grid so that you can start with few units and not collapse the complete system, right? The fault right-through is like a critical topic from the load point of view. At least at this point in time, we do not know of a solutions or an efficient solutions, right? So one way is to mitigate through some operational means that you have within the plant itself. In this particular case, we allow the unit to trip to save the system so that we can restart again, right, from the available units. So this AI-induced load fluctuation, the frequency and the UPS is one of the two critical issues that we see today that impacts system performance. Again, these issues are also relevant when we are grid connected. It's more problematic when you are islanded, but when a grid connected, this still is an issue that one has to deal with. And I think we see like for example in ERCOT and some other places. So this has been discussed, I think, as part of the working group meetings. This is kind of a summary of our learnings on different risk that we see as we start working on this islanded power supply system design, targeting the AI load. We see on the frequency event due to either generation trip or due to the starting of the AI load or combination of those. We have a frequency event due to UPS operations. We can also have voltage and the frequency transient when the load profile is running, right? When it first starts, we have a big transient, but when it's running, the issues are still exist, right? And we need solutions either through BESS or through the E-Statcom type solutions that the previous speaker talked about to mitigate those transients. And there are also issues, because the load profiles are not, is changing, right? I mean, as we speak. So there is a risk associated with either overestimating or underestimating the base size, the size of the storage that we need. The option is to have a scalable deployment of the resource that you have. So So with that, I think I'm almost time. I don't have anything new. Just to conclude, we did a preliminary round of study looking into few large-scale data centers. Like I mentioned, these large-scale data centers are large in the sense that we are talking about 1 gigawatt up to 3 gigawatt islanded systems, right? These systems are possible to operate feasibly if we design the compensation systems properly, right? Having the right side of the base, right controls, it's possible to have those kind of systems in place to accelerate the deployment of the power demand that is needed or demanded by the data center load. So with that, I like to conclude my presentation. Feel free to ask any questions. Next. Yes, thank you.